Okay, off we go. So last time we finished section 5.1. So 5.2 is going to be about this thing called double integrals. Double integrals are going to help us resolve a problem. And let me just remind you what that problem was. It was this right here. Right? We went to all this trouble to come up with a formula for how we can compute volume under a graph surface, which, I felt like we were just kind of going over all the same territory that we have in the past in single variable calculus, computing area under a graph curve. And it felt like that was, it seemed likely that was going to just kind of be exactly what we would need to solve all the other application problems that we would, of course, need to be able to answer. But we tried to compute one of these standard applications, and it just doesn't work. It really doesn't work. If you're going to argue that this actually that this makes sense, not as a conclusion, but as an argument, right, as mathematical reasoning, you've got to make sense out of that, which just doesn't make sense. And so, again, dead in the water. This isn't going to work in any practical sense. So we're going to get around this by taking ultimately a better, more natural point of view about what do we mean by a multivariable integral. Okay, so just a reminder about single variable integrals. I'm sure you all have seen this before. Common misunderstanding about this definition of single variable integrals is that it's just a kind of formal math abstracts for people who like mathematical abstractions or something like that, and it's just absolutely not true. It's half true. Okay, we do like formalities and mathematical abstractions, and that is nice about this, but that is not the only reason that we write this down, right? So let me make sure we're all clear on one of the really important aspects of Riemann sums, and that is that Riemann sums ultimately are the connecting point. They're the only way that we can get the fundamental theorem of calculus to connect up with huge amounts of applications. Desperately need Riemann sums for this. So let me try to address how this is commonly, I'm going to say, mishandled. Right? In a lot of high school calculus classes, they'll argue as follows. They'll say, well, look, if you're computing, let's say, the amount of mass on an interval, right? The classic example is mass of a rod, where you have a non-constant density of the rod. And they'll say, okay, well, step one, mass is equal to area, and then blah, blah, blah from there. And I'm sorry, that doesn't make any sense. What do you mean mass is equal to area? No, it isn't. It really isn't, right? That is not an immediate direct connection. It's just not. So now you can take the entire mass and you can say, look, the whole is the sum of the parts. There's going to be round off errors, but we're going to add up all the parts, and on any given little subinterval, mass per unit length times length is going to give us mass. And in other words, you can directly write down a Riemann sum. That you can do, right? And now a lot of high school calculus classes will then say, well, okay, I don't really like all that Riemann sum formality, so we're going to use a kind of a slicing and dicing argument, kind of copying Riemann sums to try to justify why we can interpret mass as area. And again, this is completely unnecessary. Right? We don't need to make any connections to area. I don't need to kind of deform a perfectly good Riemann sum into an argument about why mass equals area. We don't need the area at all. All we have to do is make the argument that mass is computed with a Riemann sum, recognize that integrals are Riemann sums. Most fundamentally, it is important that integrals be defined as Riemann sums. Because Riemann sums are, again, the thing that I can connect to applications, right? And once you've got that done, okay, great. You've got your answer written as an integral. Use the fundamental theorem. Bam. Done. And notice area. Not only can you not directly connect to it. You don't need to connect to it at all. If you are making an argument about computing the mass distributed on an interval, area serves no purpose in the solution to that question. All right. So anyway, this is why Riemann sums are important for engineers, for people who aren't. I'm perfectly happy to be persuaded by mathematical formalities. Yeah, I'm all about that, right? But I understand that many of y'all might not be. For those of you not interested in mathematical formalities, here's why you need to know Riemann sums. Without them, you can't answer application questions. Okay, so when I say that we want to generalize the idea of a single variable integral, this is what I mean. This is the single variable integral that we want to generalize. Forget about this question about, we asked this question that's, I suppose, a natural, reasonable, sort of naive first thought. We computed, again, area under a curve. Okay, this would seem to be a one-dimension up version of that, volume under a graph surface. And we're just barking up the wrong tree. Area, in this case now volume, not really what we're interested in. Okay, so let's actually do it now. Let's actually try to generalize the idea of a Riemann sum. Reminder, if you have an interval on the x-axis, right? Well, the first thing that we do is we take that interval, we chop it up into little pieces, like so. Right? Y'all have seen that a million times. And then you look on any individual little piece, and you argue that on that piece, depending on what we're actually computing, it's always going to be some function times delta x. And let me just kind of generalize, why is it this expression something times delta x? Or what's the broadest interpretation of this? And I claim it's usually stuff per unit size times size. All right, so let's talk about if mass were distributed across this interval here. Then the reason I would write down something like this is because I will take mass per unit length, hopefully given, and then multiply by that length, namely delta x. If I were computing the amount of work that it takes to blah, 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 I would take work per unit length and multiply by length. And whatever it is that you're computing, it's always quantity per unit size times size. And by the way, to those of you who are really attached to the idea of computing the area under a curve, you're accustomed to thinking of this as height and not stuff per unit length. Think of height as being area per unit length. It fits the pattern. This is area per unit length times length to compute area. Okay, so it's always stuff per unit size times size. And then, of course, we add up over the entire interval, and that gives us the answer to our question. Okay, so we're going to do the exact same thing here. I'm going to take my whole thing. I'm eventually going to be adding up over that whole thing, but what am I going to be adding up? Well, for any given little piece, following this pattern, stuff per unit size times size, I'm going to write down stuff per unit size times size. Now, the stuff per unit size, okay, that's going to be stuff per unit area, because now area is the notion of size, right? This is not a little piece of an x-axis. This does not have a, well, let's see here, let me say this right. The size of this little subrectangle is not described in length, it's described in area. And then multiplying by area, you see that this is a little rectangle, and that's going to be delta x, delta y. A bunch of little details I kind of glossed over there. Let me just address those little details real quick. When I slice up this area, notice I'm also slicing up the x-axis accordingly, and I get the formulas that y'all probably recognize, right? Distant, possibly repressed memories from Calc 2 long ago when you first wrote this down, right? Well, I got to keep slicing because I also have to slice horizontally, and notice that as I do that, doing my best to hit the marks there, I am also slicing up the interval from C to D on the y-axis, and that gives me some very analogous formulas there. So there's little details to be thought about. This is a worthwhile exercise to think through in your mind. It is just details, though, that, oh gosh, I don't want to say we're not going to do much with it, but these are details that are not going to contribute to specific exercises that you're all going to be solving. I think that's a fair statement, right? But these are details that make all of this make sense, so I do think it's important that you think that through. Yeah, this is just a way to make precise what I mean by chopping this up into a bunch of little pieces, and you notice this piece has width delta x and height delta y, for which I have explicit formulas, and so that's exactly what this means. Okay, now one last thing I want to say about this expression down here, and actually let me go ahead and highlight, let's see here, I will use, let's say orange for this. So our old Riemann sum, now our new multivariable Riemann sum. Students very often like to dwell on the question of, yeah, but what's f? What is f? I need to know what f is. Tell me what f is so I can understand what this means. Right? And very importantly, we're not going to say. Very importantly, for strategic importance, we're not going to say exactly what f is. Because as soon as you specify what f is, now it can only be that, and now your applicability of this idea is narrowly limited to whatever you decided that was going to be. We didn't do that here. We didn't do it in single variable calculus. We didn't specify that f has to be, just the one thing. The whole point to this construction is that f could be whatever it needs to be, appropriate to the application. There may be applications out there I haven't even thought of yet. I don't want to narrow myself by specifying what f specifically has to be. It's just, look, there's going to be some quantity that accumulates over these pieces. And however much quantity there is in one little subinterval, I want to understand that being quantity per unit size times size. So I don't know what the quantity is going to be. F will always be whatever that quantity is per unit size. Yeah, sure. But what the quantity is, who knows? And likewise here, what is it that we're adding up? Are we computing a bunch of mass? Are we computing the population of Wyoming? What is it that we're adding up here? I don't know. Let's keep that wide open. The less we specify, the more broadly our tool applies. Okay. But again, always remains f here. Our future integrand is stuff per unit size, so that I can multiply by size. Okay. All right, so having set all that up, this makes our definition of what we call a double integral, totally analogous to a single variable integral. And this is the notation we're going to use. I think the notation is reasonable. Don't make the mistake. Actually, let me erase that because that's deceptive. Don't make the mistake of thinking that this is a single variable integral of a single variable integral. That's not what that means. Very importantly, not what that means. This is I guess you could say, inspired by the single variable integral symbol, right? We're putting two of them in recognition of the fact that we are adding up over two different indices, representing that we are going to be adding up in two different directions. We have to add up left to right. We also have to add up, down, in order to get all of these pieces, right? I got to get the whole population of Colorado, let's say, right? So you got to add up in both directions to get all of that. So that's why we have the two integral symbols, but I want y'all to think of this as a single symbol. This does not say single variable integral of a single variable integral. That's a different construction. Okay, how we doing? Everybody happy? All right, good news for y'all. This is not a course in real analysis. where it would be appropriate to talk about irregular partitions and test points and many other things in that general direction, because frankly, we are sailing over deep water right here. There is a tremendous amount to say about how to define integrals, and that's a cool class. And if you're ever interested, if you're looking for beautiful classical mathematics, analysis is, it's hard to argue. That's kind of that's the Mozart of pure math, right? Is analysis. So beautiful stuff, and I wish we had time, but we don't, and that's just not what this course is about. So y'all do not have to worry about irregular partitions and test points, and I believe that's reflected on the content syllabus. The reason we're ignoring it is because we're going to focus all our attention on continuous functions. And it turns out that when you have a continuous integrand, none of that stuff matters anyway. So it's a convenient bypass of a tremendous amount of stuff. All right. Okay, let's do an example. Classic first example. Arguably a silly example. We already know how to answer this question. Right? Notice the question says, suppose you're looking at a graph of a function of two variables, and sitting over a rectangle, the question asks us to find the amount of volume under that graph. We already know how to do this. We did this with iterated integrals. There. But let's do it again. You'll see why momentarily. I can write down the volume of some little piece there. And that volume, I argue, is height. Height being, of course, f of xy, times the area of the base. So down here at the bottom, you can imagine that that's a little area of our domain. And, of course, we've written that as delta x, delta y. Boom. All right, we've got ourselves a double integral. This is just, in fact, character for character. That is the definition of a double integral. So double integral is another sort of way that we can address this matter of how to compute the volume under a graph. All right, is that cool? Let me show you why this was a important first example of how to use a double integral. When you compute something two different ways, your two answers have to be equal to each other. Really clever move. This happens multiple times in math. So again, we've previously computed volume with iterated integrals. Now we've computed that same volume with a double integral, and because we're computing the same volume, that means that these two answers must be the same. So turns out this is the big payoff. The big payoff is not that we know how to compute volume. I've already tried to make the case that ultimately that's not really that interesting of a question. It's a nice visual aid. Okay, I suppose that's cool in its ways, but it's a distraction from the point. Double integrals are going to end up being what's really important. And we've just established that you can compute double integrals with iterated integrals. So that gives us the following strategic sort of roadmap here. And every time y'all do an application question, I want y'all to be thinking about this roadmap. I'm going to walk you through everything that's on this little roadmap. Going to sort of go in chronological order, everything we've developed with integrals so far. Oh, yeah. Mm-hmm.
I'm just a bit confused on what we just previously said, like the very last thing.
Mm-hmm. Yeah.
Can you just please go over that? Like the fact that they're equal?
Yeah, sure, because we were computing the same thing. So we've previously computed volume with iterated integrals. That was last time. And what we just did up here is we computed the exact same volume and got that it was a double integral. Now, if you compute something two different ways, you have to get the same answer both times. And that means, because we're all computing the same volume in both cases, that those have to be the same.
And is there like do we have to use like specific methods for specific cases, or like both work at any time?
Well, it's going to turn out, I mean, here's the bad news about double integrals. We don't have any methods for how to compute them. This is just a great big Riemann sum, dead end. We don't have a fundamental theorem of calculus for double integrals, right? So, in most cases, this isn't really an option for computation. Yeah.
Thank you.
Right. A few exceptions here and there. All right. Yes.
What is the point of writing out a double integral if we don't know how to compute it?
Yeah, because we now know that I can compute it with iterated integrals.
Okay.
Yeah, that's right. So that's you're anticipating what I'm about to talk about. So let me just go ahead. Yeah, you're just a little ahead of me. Okay. All right. So here's the connect the dots of all of the ideas we've talked about. Okay. The first thing we did is we asked, how do I compute volume under a graph? We motivated iterated integrals. We talked about how to crank through with the fundamental theorem. And I'm going to say all of this was our sort of first attempt, which worked for one application question, namely how to compute volume. Okay. And then we had a crash and burn situation. We asked, hey, can I use this idea to compute, let's say, mass? And I tried to make an argument that would directly connect mass to iterated integrals. And it just didn't work. The pieces didn't fit together. I was multiplying mass per unit area times length, and that's not a thing. Right? So that just doesn't work. And likewise, by the way, of course, you can't just immediately claim that mass is volume, because no, it isn't. Right? That might be a conclusion. It's certainly not valid reasoning. Okay. So that's where we were a few minutes ago. Then we came up with this idea of a double integral, right? Developed, kind of copycatting off of a single index Riemann sum, and our first example was that I can compute volume as a double integral. And then I remembered I've already computed volume with iterated integrals, and then we celebrated this little convenience that you can always therefore turn a double integral into an iterated integral. And now, all we have to do then, if you want to actually solve some application question, whatever application question that might be, 3-step process. Step 1, write it as a double integral. We'll be writing down stuff like mass per unit area times area, or work per unit area times area, or population per unit area times area, right? All these kinds of connections between application questions, turning them into double integrals, that's all going to work fine. Next, we're going to rewrite double integrals as iterated integrals, as we just established we can. And then we're going to take our iterated integrals and we're going to plug and chug with the fundamental theorem and get answers. And this is how we're going to make arguments about computing stuff with double integrals. 3-step process. Everybody good? Okay. So again, it's very important to make the distinction between double integrals and iterated integrals. Iterated integrals, I can compute. We need iterated integrals. Being able to compute stuff matters, right? You can't compute double integrals immediately. That's disappointing. But sort of symmetrically going the other way, you need double integrals to be able to connect to applications. You can't just immediately connect your applications to iterated integrals. So these have sort of complementary utility. Double integrals serve to connect to applications. Iterated integrals serve to be plug and chuggable. So really, really valuable that it, of course, as we've already said, really valuable that we can always say that they are computationally equal. Okay. All right. Okay, let's do one. Again, 3-step process. By the way, this is the example that we crashed and burned on last time. Oh, let me hit the button. There we go. Okay, compute the mass on a rectangular sheet, right? And again, terrible failure last time. We tried to multiply mass per unit area times length, and the whole thing was just a catastrophe. Okay, step 1. This is a underappreciated little step right here. This is just the recognition that mass has a key feature, I'll say, and that is what I like to call an accumulating quantity. Namely, the whole is the sum of the parts. Right now, people trot that out as a trite phrase in a lot of cases, but it's really important here because that is my first step. I am going to argue about the whole mass by looking at individual little pieces of mass and claiming that if I add up the pieces, then I get the whole. Right? So you'd better be talking about some quantity that actually behaves like that if you want to be able to use that critical first step. And a lot of people kind of roll their eyes. Well, come on, doesn't everything have that feature? No. Oh, no, not everything has this feature. Perimeter is my favorite little sort of counterexample. If you look at a whole, you look at its perimeter, and if you cut that up into a million little pieces and you add up the perimeters of all of the million little pieces, those million little pieces, the sums of the parts is going to be way more than the original whole. So not everything this is worth appreciating, right? That mass truly is an accumulating quantity. Okay, and then it's kind of all over because mass is mass per unit area times area. And this is the very definition of a double integral, and we have now successfully completed what I like to call step 1 here. Let's see if I can get all this on. There we go. Step 1, we have turned a question into a double integral. All right, step 2. Turn the double integral into an iterated integral. Yeah! As discussed previously, we've already established that works. So that you just have to write it down. Right? And of course, you got to be careful about range of values. This right here says that x ranges from a to b, and so notice that my x bounds are from a to b, and likewise for the y bounds. Okay. All right. Yeah.
Wait, how'd you do the balance?
Yeah, so you just have to look at the domain. The domain here, this says that the range of values of x on my domain is from a to b. And so in my iterated integral, my range of values of x is from a to b. Yeah. In other words, if you just look at literally the rectangle at hand, x goes from a to b. Yeah. Yep.
How is this final step 3's iterated integral? How is that different from the one we had the other day, which didn't work?
I'm not entirely sure I understood the question.
Isn't that what we wrote on Monday?
Oh yeah.
You can't do?
Oh yeah. No. So and again, this important distinction here, right? There's a difference between a statement being true and a statement being clear, right? We're interested in the reasoning, not the punchline. Now, it is true that the mass, yes, it is equal to the iterated integral. But that is not a single first step, right? This does not work as an elemental sort of piece of reasoning. There is a critical step in between there that makes it clear why that's true. Right? So again, now I know it's very hard to kind of digest this idea, but you kind of try to get rid of this idea that it's all about the answer, and if you get the answer, then it's right, and that's what right means, is you get the right answer. No, we're doing reasoning, right? And so the reasoning just doesn't follow. If you try to make an argument about why mass is an iterated integral without using a double integral, you're going to have a lot of explaining to do oh man, that's going to be a rough one. And it just doesn't work as reasoning. You see where does that make sense? Yeah. So it's a very subtle point, and it's a good question. Again, a lot of people kind of miss out on that point. Yes.
How would you know your bounds if you didn't have it?
If you what now?
How would you know your bounds if you weren't given it?
Well, you have to know what the domain is to be able to even ask the question. Yeah. So that has to be given. Yeah. Right. Yeah. Okay, all right, so let's see. Let me remind us what we did. We turned it into a Riemann sum like so, and then we turn a double integral into an iterated integral. That's this right here. And then once you have an iterated integral, plug and chug with the fundamental theorem of calculus. Y'all have done that several times anyway, turning iterated integrals into answers by integrating from the inside out. Yeah.
I just wanted to ask, in terms of application, does this not assume that density is equal to 1 at all times?
No. I hear you. This is saying right here that this density that we're given, this is mass per unit area. And notice all I'm saying is that whatever formula this is, and it could be all kinds of weird, it's got to be continuous, right? But as long as it's continuous, whatever it is, mass per unit area times area will give me mass.
That makes sense.
So that's where that's happening. Yep.
And then does that negate the v equals the double integral, the volume?
No, there's no volume in this question.
Okay. So
Yeah.
where does volume come into play?
Volume has served its purpose and is no longer necessary. Volume's purpose was to help us make this connection, and now that it's done that, we're going to pretend, I like to pretend that volume isn't really a thing, right? And all we're doing is we're doing this 3-step process now where we're going to go boom, boom, boom. No volume needed at all. Yep. Okay, last one, then we got to go. Yeah.
So we said that delta x times delta y would be equal to the area, like
Yep.
d of a, but that's because it's a rectangle. What if we had like a different shape?
That's right. So we're always going to break things up into little rectangles,
Okay.
but there is a related question, which is, can you do that? And what if your actual domain is not a rectangle?
Yeah.
That's something we're going to address soon.
Later on. Okay.
Yeah.
Thank
Right.
you.
Yeah. Okay, so that's the 3-step process. Again, can't emphasize it enough. Think about when you're doing exam questions, right? If you want the full credit, which I think you do, right? You got to keep in mind what we're looking for, right? We're looking for valid mathematical arguments. We're not just looking for the right answer at the bottom of the page, right? And a valid mathematical argument has to show all 3 of these steps. Because if you take any one of these out, then your argument has this gaping hole that it just doesn't work, right? So make sure that you explicitly show all of those steps. Now, what you may do is perfectly fine. You can streamline this in a couple of ways. If you want to just go straight from here to here and just kind of gloss over all of this stuff, yeah, okay, that's fine. We're going to do enough examples of this kind of thing where, the assertion that mass is a double integral of density is going to be, I think, comfortably established, and you don't need to show those intermediate steps. I showed them here just to be explicit as to why double integrals work, right? That's kind of for sort of teaching purposes. So that's one little streamlining, and then of course the very next thing you would write down would be the iterated. Would be the iterated integral, and then you would compute with the fundamental theorem, right? So you can just say mass is that, which is that, and then compute with the fundamental theorem. Totally fine, full credit, right? But if you leave off the double integral, you're gonna take a hit, because that is an important part of the reasoning. Having the double integral written down is what distinguishes the perfectly acceptable dark blue argument from this nonsensical red argument down here. Does everybody see that? Okay. All right, second little streamlining thing I'll point out. You eventually notice, after you've been down this road enough times, that this turns into an integral. Effectively, this kind of is, in some sense, what turned into the double integral symbol. And why don't we just kind of use that immediately? It's kind of convenient. Right? And then likewise, you eventually notice that, okay, well, yeah, the deltas eventually turn into D's, so, okay, why don't we just do that from the start as well, right? So this is a shorthand. This is sloppy. This is writing stuff down that hasn't really been defined, but if you want to write this, to, again, streamline is fine, right? Again, I haven't defined what I mean by this notation here by itself. Not defined anywhere in the notes, right? We defined this thing. I haven't defined this thing. But at the same time, everybody knows what you mean when you write this. It's very standard shorthand. It's very convenient. And, you know, this is just one of these things where we just accept a sloppy notation. Okay. All right. Okay, moving along. This example here is just really an example in that shorthand notation. Most of what you see here is plugging and chugging a bunch of algebra arithmetic that y'all can read. I'm not going to go over that part of the problem, but I do want to talk through the sort of the development. So the big idea is we have a wall here. I wrote this question when my house was being built, and there's a sort of on the front facade, there's this kind of wall area where it's one of these stone facade kind of things, right? And as the guys were building it, I was just watching them pick up these heavy bricks and having to pick them up off the ground and put them in there, and it occurred to me, that's a lot of bricks. And they're doing one at a time, but all together, that's a lot of work. Glad I don't have to do that work. So how much work did I successfully get out of there, right? What was the grand total amount of work? It's a reasonable question to ask. And so what we're going to do is we're going to argue first that the whole is the sum of the parts. In other words, if I were to look at any individual little brick there, right? If I can address the question of how much work it takes to pick up that one brick, it was on the ground, I got to pick it up all the way, lift it all the way up to here. How much work did that take? And then I can add that up over all the bricks. Right? So work is an accumulating quantity. The whole is the sum of the parts. Cool. Let's talk about that one brick. Well, that one brick, this one brick right here, work is force times distance. Right? This is a differential amount of work. This is an amount of work that's part of a larger whole that I'm sort of adding up. Right? That amount of work, I'm lifting something a certain distance, which is y. And what is it that how much force am I applying over that distance? Well, however much that brick weighs, and this is a differential amount of weight. Force is weight, of course. Differential amount of force because this is a differential amount of work because it's just the one brick. Does that make sense to everybody? Okay. Now, I could have written this with Riemann sum notation and just be a little bigger and bulkier and a little bit more annoying, but very convenient streamlining. And so, again, that's kind of my main point here, is this makes for a very convenient shorthand as we develop the integral that we're eventually going to have to crank out. So let's see, the other step that this uses is that pounds, right? By the way, you all remember the whole annoying feature of how in the U.S. we conflate mass and weight, and it's really unfortunate, and oh well, what are you going to do, right? So how much is, if I want to talk about the mass of that chair, a lot of places they tell you how many pounds it weighs. They're not going to tell you the mass, they're going to tell you the force, right? So we're accustomed to thinking of density as being mass per unit size. Very often it is force per unit size. That's just how business is done in a lot of contexts, unfortunately. So so all this says here is that weight is weight per unit area times area. So again, very conveniently streamlined by writing it down with this differential shorthand. All right, and that's all over but the shouting. Y, let's see here, density was given. dA, of course, is dx dy, and lo and behold, I now have an iterated integral, and y'all can crank out that iterated integral. Make sure you can do that, by the way. Right? Careful. Good to check. Yes?
Isn't there also a G in the force?
If you want to relate force to mass, then yes. Force is mass times G if you're at the surface of the Earth. But the point is, we were given, I guess I didn't write this explicitly, but this density here was, I said it in words, is force per unit area, not mass per unit area. So I don't have to multiply by G. The G is already hidden inside of that expression.
Okay.
Yeah. Right. Okay. All right. Natural next question. Somebody already asked this question. I've forgotten who it was. But what if our domain is not a rectangle? And there's a couple things that have to get said here. The first is I have to address the question of a double integral. Can you define a double integral on a non-rectangular domain? Let me zoom in to the domain here if I can. Okay, now there we go. And there's so many, this little annoyances, like, I mean, as I slice like this, and then I start to slice, this way, and notice some of these pieces aren't rectangles, like that little piece right there is not a rectangle. Is that okay? How do we deal with that? Blah, blah, blah. That can all be dealt with. It's a bunch of formalities. It's very cool formalities. This is what real analysis will address, right? It's very interesting, it's very cool, very worth it. It's not what this course is about. So what I'm going to say here is that if you want to define a double integral over a non-rectangular domain such as this is, totally doable. Not what this course is about. And the good news is it still means exactly what you think it means. In other words, it still means that we're going to take this area and we are going to break it up into little pieces, and we're going to talk about on each piece some sort of quantity per unit area times area. And it's fine. So again, this is dealing with those formalities is not our job. The takeaway for us is, yes, you can talk about double integrals. It totally makes sense. It's exactly what you think it is. Don't worry about it. That's going to be our upshot. And if you want to hear more, take Math 431 or 531, one or the other, depending. Okay. All right, so next question, reasonable next question. Can I compute this with an iterated integral? And okay, well, let's think it through. This will the volume under a graph example is very convenient to give us a picture to look at. If I want to compute that volume, can I add up a bunch of different slice volumes? Well, yeah, of course. I slice up weird shaped loaves of bread all the time. And yeah, the volume of the loaf of bread is the sum of the volumes of the slices that you make. Right? It doesn't have to have a rectangular footprint. All good. Can I compute this area of this slice as, can I compute the volume of this slice as area times thickness? Absolutely. Can I compute the area with an integral? Is it area under a curve? Absolutely. Everything goes through pretty much the same, right? There's very little different. Let me show you the only thing that's really importantly different. Only thing, if I can get this thing to cooperate, here we go. Only thing that's different. When I look at my x integral, when I look at, x going across here, for the purpose of computing that area with an integral, right? The only thing that's different is how I understand, for example, the starting point. As again, x is what's going along. I'm moving in the x direction. Where do we start? Well, this point is why I'm starting at that value that I'm calling A. But notice, if I were looking at a different slice, that starting point would be here instead, and then instead of having that value as my starting point, I would have a different value as my starting point. So the punchline here, and again, this is one of the only differences when you have a non-rectangular domain. These slices are computed as integrals over different intervals depending on which slice you're looking at, and so you have different bounds, and so those bounds for the inside integral are functions of the outside variable. They depend on which y, namely which slice you're looking at. That's the only difference. Is that cool? Here's a bit of good news. You look at this picture motivating this conclusion that I'm claiming here, and not hard to persuade yourself that whole picture takes place in the XY plane. Nothing about height is at all relevant to that, right? The F is the height, and yeah, sure, that's the same. But understanding, how do these bounds change? Well, these bounds change based simply on looking at the domain itself. You don't need the three-dimensional picture. This is a case where interpreting what we're doing with the volume question is actually making our life harder, not easier. It's forcing us into drawing these weird three-dimensional pictures and dealing with perspective and stuff like that, right? It's super hard. When we didn't need to. All we really need to do is to understand the domain itself. Right? So here's that same domain. Let's see here. And for a given value of y, right, as we were going in the y direction, for a given value of y, we have a slice. X is going to go sort of across like that. And if you want to know what the starting bound is, well, we're going to look at that point right there. And if you want to know where x ends, right, keeping in mind this is going in the x direction. If you want to know where x ends, well, x ends when you get to that point right there. I don't need to draw f. F has nothing to do with the bounds. Okay, so the pattern, what we're always going to do to find these inner bound functions goes as follows. Let me talk about the lower bound. You want to find this lower bound? Identify what the corresponding point is. Recognize from the picture, you're going to need the picture, by the way, but recognize from the picture what the curve is that defines that point in the first place. Right, so for whichever bound, identify the corresponding point, identify the curve that defines where that point is. Of course, that curve will have some equation. And then remember, okay, yeah, and furthermore, the value I'm looking for is a value of what variable? Right here we're looking for this a of y. That is an x coordinate. It's a bound for my x integral. And so in the equation you've just found, solve for x. So solve for what you need. Yeah?
What if it's like asymmetrical curve?
Well, yeah, it very often is. Yeah, no, things can get a little weird. We're going to see a bazillion examples, and ultimately the punchline is it doesn't matter. It's all good. So let me show you how am I doing on time? Okay. All right, we don't have time to do the example. Okay, I'll end just a few seconds early. I'm sure I owe you the time. See y'all later. Have a good rest of your Wednesday. See you on Friday.
Thank you.
All right, yeah. Don't forget about attendance if you came in late. Yeah, sure.